Hi, welcome to Ordinary Differential Equations. Today we are going to have a lecture about integration by parts. This is something that you have seen in calculus, and so today it's going to be a review of that topic. So let's get started. What we have in mind is a so-called multiple integration by parts, sometimes referred to as ladder method or tabular method. What I'm going to write is going to be the same as those, except that it's written in a line as opposed to written in a table. An example of this problem would be something like find integral of t cubed exponential of 2t dt. Of course, this is something that you do by integration by parts, and what happens is that you have to do that several times, keeping track of sign flipping and all the coefficients tends to be error prone, so that's why it's recommended you write a table or you write as we are going to talk about today. So let me get started by introducing some notations. If I have a function, say f, and that is say t to the power of 5, then of course you know very well that the derivative of it is 5t to the power of 4, and the second derivative of course 20t cubed, and the third derivative is 60t to the power of 2, and so on. Fourth derivative 120t. Fifth derivative is going to be just 120, and then sixth derivative is just 0. So one thing you notice that if I have a polynomial of degree 5, by the time I take sixth derivative out of it, I'm going to hit 0. If you take one more level derivative than the highest power of a polynomial, you do hit 0. We are going to make a notation for this thing that's going to be a little bit more civilized than just putting tick marks. We take a look at the right hand side. We notice that the power is going down, so we are going to call this thing down operation. Down operation, so f down simply means the derivative of f. And then this would be f double down. Instead of putting two arrows and getting stuck with this same kind of a issue that we had here, we are going to put a 2 to indicate that we took f down twice, and so on. So this is going to be triple down, or f down 3. This is going to be down 4. This is going to be down 5. So when we say down 4, the power has come down from 5 to 1. It has come down 4 steps. And this, of course, is going to be 6th step of this process. Well, of course, if I was going to integrate, the process would be the opposite. That is, the power is going to go up. So if I have a function, let's call this one, say g, say exponential of 2t. The integral of g, I'm going to drop dt so that it's not going to be crowded. So integral of g, of course, is exponential of 2t over 2. I can have a constant here. Just going to clutter the situation, and we want to have something that is not error prone, and that constant is not going to add anything to our array, and so we just leave it out in this case. I'm going to call this thing the up operation, due to the fact that if this was a polynomial, when I integrate, power goes up. Well, of course, I can take the integral of the integral, meaning take the integral of this expression, and of course I'm going to get e to the power of 2t over 4. What we have in mind here is to write this thing as g double up, and if I take this integral 3 times, again in all steps we are ignoring the integration constant, We could have included it, but it would have just cluttered the situation. This becomes G triple up, and so on. Well, this notation is going to help us write the integral of expressions of this type in a single line and be done with it quickly. Let me go ahead and remind you of integration by parts problem. If I have an integral of a function times another function, again I drop the differential just so that we have a formula that is brief. We can write this thing as f g up minus integral of f down g up. Now I invite you to write your standard integration by part formula, and notice that these are actually the same thing. We are making up this notation so that when we want to repeat this process, we'll have an easy time remembering all the steps and be able to do it quickly. So sometimes you have to do integration by part twice. In that case, this formula becomes f g up minus f down g double up, and then final piece is the integral of f double down g double up, and so on. If you need to go through the integration by part 3 times, the formula you really need to use is the following: is f just like starts like before, so f down g double up. So f is going to be going down and g is going to be going up. And you might be asking, well, how do you choose who is going to go up and who's going to go down? Well, actually that is a standard question in integration by parts. In simple cases, one of these things is a polynomial and the other one is some other function, and typically it is to your advantage to take the polynomial and take it down, because eventually the polynomial is going to hit 0, and the very last term in this process is going to be integral of 0. Integral of 0 is a constant. So provided that the other function integrates easily, that would be a standard process to go through. So you notice that f starts as itself, then down, then double down, and so on. G immediately is taken up, and then up again, and then the last stage stays the same. So let's go ahead and write this thing. The next term is going to be f double down g triple up, and what should be the last term here. So let me ask everybody to think. So it's going to be our standard process in this course that I will put a picture up and ask you to think about what is it that we are supposed to put at the next stage. So I hope everybody thought about that, and I'll continue. So what did you think? I'll put here minus. It's going to be at the last stage they are evened up, so it's f triple down and g also triple up. Okay, now let's see. So now you try. What would be the next formula for this if I want to go one more round? So we are going to hit 4. So again, I'm going to pause, and I expect you to write the whole thing based on a pattern that you see. The pattern is very easy. The signs are flip-flopping. F is taken down, starts at F itself, and then F down, double down, triple down. The one that's going to be taken up is immediately taken up, and then goes up, up, in the last stage stays the same. So it's 3, and that's 3 in the last one. They are always taken up or down by same number of notches. Okay, so you are going to write for me what would be the same thing if I do it 4 times. So, of course, it's going to be F. It starts exactly same as before, so nothing is different. F down, G double up, F double down, G triple up, F triple down, G quadruple up. Then the final is going to be now plus F quadruple down, G quadruple up, and so on. We can also write the general formula. I leave that for you to write this thing so that it ends with n rounds. Well, how do we know how far to go? It all depends on what kind of a problem you have to begin with. So if I have something like t cubed exponential of 2t, I know that if I take t cubed down 4 steps, it's going to be hitting 0. So a polynomial of order n, if you take it down n plus 1 steps, it's going to hit 0. So that is something to keep in mind. So when I'm dealing with this thing, I know I better go as far as 4, because for function t cubed, if I take it down 4 steps, it hits 0. So let's go ahead and do this. So let me start from this side. I have the integral of t cubed exponential of 2t, of course, differential of t, but we just dropped all of that to avoid the clutter. So I'm going to wrap these things in parentheses so that we don't run things into each other. So this is going to be taken up, minus t cubed is going to be taken down 2 notches, exponential of 2t is going to be taken up, excuse me, let's see, this is t cubed is taken down, exponential of 2t taken up 2 notches, and then plus t cubed taken down twice, exponential of 2t taken up 3 times, minus t cubed taken down 3 times, exponential of 2t taken up 4 times, and finally is this one, which is t cubed taken down 4 times, and exponential of 2t taken up 4 times. So if I'm writing t cubed exponential of 2t, this is t cubed, take it up, e exponential of 2t over 2. Take that, differentiate, 3t squared. Take that, integrate one more time. Do not put any constant to avoid clutter. So antiderivative of exponential of 2t is going to bring us another 2 in the denominator, so it's going to be 2 squared. Now take this thing and differentiate one more time, so it's going to become 6t. Take this one and integrate one more time, which is exponential of 2t over 8, or 2 cubed. Maybe I just go right, so that's easier to read maybe. This is going to become 8. Derivative of this one is going to be 6. Antiderivative of this one, exponential of 2t over 16. Derivative of 6 is 0. Antiderivative of this, whatever it is, we don't really need to write it, but for completeness, I write that 2. This is 0, whatever it is, so I don't really need to calculate anything inside the last one. And antiderivative of 0, in this case, we do write the constant. So final answer, t cubed exponential of 2t. Now let me go ahead, be complete. So it becomes t cubed exponential of 2t over 2 minus 3t squared exponential of 2t over 4 6t exponential of 2t over 8 minus 6 exponential of 2t over 16, and now we put the constant. Same approach can be applied to some other cases that are a little bit more involved. For example, for calculating exponential times a trig function such as sine or cosine. I'll have a write-up on my website. You can consult that for more detail. Okay, until next time, good luck and God bless.